Hello and welcome to the Daily Space for today, November 26th, 2018. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. We have a new setup. I am trying a blue screen. I am learning that it looks like my microphone is sort of appearing out of nowhere, so we may need to change the setup just a little bit. We are 1 hour away from the landing of NASA's InSight space probe on Mars. I will be following this broadcast up straight away with coverage of InSight. So please stick around after the news, after the questions, and we will go to bringing you information about whether or not this little lander lands. Now, a few quick words before I get started with today's science. We have a new home. This show, as well as everything else that you see here on Twitch, is brought to you by the Planetary Science Institute, working in collaboration with Youngstown State University. I am a new senior scientist at the Planetary Science Institute, and they have provided a new home for all of our media content. And starting January 1, all of CosmoQuest is moving over to the Planetary Society. Unfortunately, we found out that our grant that funds the majority, but not all of CosmoQuest, is also going to be ending December 31st. These two things are not related that we know of. We had previously been warned that we might be dealing with cost cuts due to the overruns of the James Webb Space Telescope. We hadn't quite been prepared for those cuts due to James Webb to, zero our budget. In order to try and bridge the salary of all of our staff, who are mostly students and junior researchers, we are in the process of doing a massive fundraiser. I personally am going to only be paying myself off of any grant money that I'm able to bring into the project. The money that we are raising is to pay for human beings. It's to pay for, some of the people you see around on this channel. So if you have anything to give this holiday season, please help me put together a Christmas miracle so that I don't have to, lay off my entire team. So you can see the goals below. You can see all the ways you can help below. And I'm going to be bringing this up at the beginning and the end of the show. But in the middle, it's going to be all about the science. So today we have a whole variety of stories coming to us near and far, and let's click on over to the first one. This is a story of compact galaxies. You can see them here where the arrows are, and I'm not very good at this green screen thing yet, so you can see them in different places in the image as my hand goes off the green screen. I will practice that more in the future. These compact galaxies, these are objects that are in some cases more massive than our own Milky Way galaxy, but occupy significantly less volumes in space. This means that they are super luminous because all those stars are crammed together and all their light is coming out of one small area on the sky. These objects, in some cases, were among some of the very first galaxies to ever form in our universe. In a new study led by Fernando Bortrega of the Instituto de Astrofísica y Ciencia de España and the Facultad de Ciencia de Universidad de Lisbon, or put differently, the Faculty of Sciences at the University of Lisbon. Fernando Bortrega, he and his team made observations and found 29 new ultra-compact massive galaxies. These galaxies were all found in the not too distant universe. They were found between 2 and 5 billion light years away from Earth. And in looking at these galaxies, they looked at them through a variety of different filters that allowed them to say, these galaxies have this much light in red, this much light in blue. And by subtracting off how much light was received in the different filters, they were able to very precisely measure the color of the galaxies. Now, that may not sound all that exciting to start with, but the thing is, the color blue is specific to star formation in galaxies. If you see a system that is blue, it means that there's stars that are only millions of years old. In looking at these systems, they dashed out of their sample anything that showed signs of blueness, leaving behind only systems that were, as we put it in astronomy, very red and very dead. These are systems that only have the oldest stars remaining, the red dwarfs and red supergiants that are the remnants of larger stars and the smaller stars that never really die. In looking at the 7 systems they found that were very red and very dead, they were able to determine that these are likely primordial systems of galaxies. These are systems that have been around since, well, pretty much the beginning of galaxy formation. Now, one of the interesting things about these systems is they're not located, as one might expect, in the vast voids of space. Most galaxies exist in pairs, in groups, in clusters. And in these smaller systems, when 2 galaxies pass, because there's not a huge gravitational influence on them, they pass very slowly. They orbit very slowly. And in these long crossing times, in the long periods of time it takes for 2 galaxies to go from interacting to not interacting, a lot of damage, a lot of disruption can occur during the interaction. Well, in massive systems where there's a lot more gravitational interactions going on, things are orbiting much faster. There's a much larger gravitational well in these massive clusters. And it turns out in these massive clusters where systems pass very quickly, you don't have a lot of disruption occurring. And these primordial massive ultra-compact galaxies are primarily being found in high mass systems where the crossing times are short and the distortions few. Now, finding these systems is only the first step. We now know here are 7 pristine systems that we can use to understand the first galaxies. The team that discovered them is now requesting time on some of the world's largest ground-based telescopes. So here we're talking about the Very Large Telescope in Chile and other similar systems scattered about the world. And using these massive telescopes, they're going to gather in all the photons they can and help us build up a picture of how galaxies formed in the early universe. Now, galaxy interactions, they keep happening throughout all of history. And this is a much closer system. Here, the image has been reversed. Black is white, white is black, to allow you to see finer grade structures. This is then overlapped with high resolution images taken in a single color. These images were taken by a team working in Israel, Russia, and the United States, led by Noah Broash of Tel Aviv University. This is a set of interacting galaxies that have gotten strung apart and disrupted during a slow, small group interaction. This is the opposite of the systems we were talking about a moment ago. This particular system that we're looking at is located about 300 million light years away, and from the tip of that tail in that interaction up to the end of its tadpole-shaped head, this entire system is about 1 million light years in length. This makes this system of galaxies 10 times longer than the Milky Way is. What we're seeing in this system is two regular disky galaxies, and a very disrupted, otherwise invisible dwarf spheroidal galaxy. This is Hickson Compact Group HCG 098. L at the end. It's one of those interesting places where, because this compact group only has these galaxies in it, we're here able to see what happens when you have pristine interactions. So quite coincidentally, we get two stories coming out the same week that tell us stories on opposite ends of the galaxy evolution spectrum of possibilities. This particular interaction with one dwarf and two regular galaxies allows us to see exactly how that dwarf can get shredded, disrupted, turned into this long, complicated tidal tail. Now, one of the things that I find particularly amazing about this research is, while the images that we're looking at have everything painted quite blue, the images were taken through a filter that was quite red. It was designed to block out all the light pollution in the sky where the observations were made. And these are observations that were made in Tel Aviv and in California, two very light polluted places. And the telescopes that were used weren't that big. They were only about 70 centimeters in diameter. So here we're looking at the kind of system where your mirror is less than a meter across, and there's many amateurs out there that own telescopes this big. What made this research possible was diligence. They had a special filter that blocked out the specific colors of light pollution, and then they just took image after image after image and very carefully combined all of those images to get the results that we see here. And now it's up to the dynamicists, the people who model these kinds of systems, to figure out how exactly did these systems start out? What were the original orientations, and what was the angle of attack that allowed these systems to collide and take the shape that we see today? Now, continuing our journey, moving inwards towards our own solar system, we have observations of a star-forming region that were taken with a new instrument on ALMA, the Atacama Large Millimeter Array. And here we're kind of stretching millimeter to the limits of what one might call millimeter. This is an observation that was taken using a Japanese-made instrument that is designed to observe in frequencies from 787 to 950 gigahertz. Converting that over into wavelengths, these are observations that were made right around 0.3 millimeters. The instrument was, as I said, built in Japan, and the results that were examined were observations made by chemist Brett McGuire. Now, the chemist came into play because in this kind of spectroscopy, what we're looking at is emission lines. Thank you so much, Dat Dolphin. What we're looking at is a whole variety of emission lines created by molecules. As light from the hot, bright stars in this system emanates out through the cloud of gas and dust, well, that light gets absorbed by molecules and then re-emitted in the specific wavelengths that an excited molecule gets excited into. Now, in this case, we went from looking at this system with Herschel and being able to identify just 65 molecular emission lines. In this case, the black line that you see in this data, the black line, it's over there. The black line that you see in this data, that is the Herschel data flipped upside down, so you can more easily compare the two data sets. That black was the best we'd been able to do up until ALMA got the new receiver turned on. ALMA's data is shown in blue. There are 695 molecular lines here. And this is why we have chemists. Chemists working in the laboratory, well, they heat up, they illuminate a variety of different molecules to find out what are the emission lines that relate to different complex combinations of atoms. By comparing those laboratory spectrum with what ALMA was able to observe, we've been able to figure out that this cloud contains methanol, ethanol, methylamine, glycolhaldehyde, and let me try saying that again, glycolaldehyde. I'm an astronomer, not a chemist. What that last one means is they found simple sugars. There are simple sugars out in the regions of space where stars are forming. Now, if you wanted to go out and look at this system, it's a small corner of the Cat's Paw Nebula. That's NGC 6634, and this is the L cluster, the L knot in that cloud of gas in the Cat's Paw. This particular system is just 4,300 light years away. I just love the fact that space is filled with sugar. And we know that thanks to a telescope up in the dry Andes Mountains in Chile. Now, continuing to move towards smaller and smaller things, we have an update on the TRAPPIST-1 system. Now, it was hoped when TRAPPIST-1 was found that by now we'd have observations made by the James Webb Space Telescope that would allow us to understand these Earth-sized planets orbiting a red dwarf star. In the absence of James Webb actually launching, what we have instead is a new set of theoretical models that sought to, well, look at how that M dwarf star would have evolved over time and how its evolution impacted those Earth-sized planets that orbit around it. This is research that was done at the University of Washington, and the lead author on the paper is postdoc Andrew Lukowski. Now, what this team found is that, and here I'm going to quote the press release, due to an extremely hot, bright, early stellar phase, all 7 of the star's worlds may have evolved like Venus, with an early ocean that may have evaporated, leaving dense, uninhabitable atmospheres. However, one planet, TRAPPIST-1e, could be an Earth-like ocean world worth further study. Now, the caveat on all of this is the may. These are systems that may have evolved like Venus, but space may have found another way. And that means these could be more water worlds, they could be more complicated than this. But what we're considering now as a good starting point is the worlds closest to this star. They dealt with high temperatures early in their life. This caused a great deal of the water on the world to evaporate into the atmosphere. UV light from the young star then split those water molecules apart, causing the oxygen and the hydrogen to be separated. The hydrogen, when struck by solar wind from that young star, would have gotten blown away, making it impossible for that water to reform into water, leaving an artificially oxygen-rich atmosphere to these planets. Now, oxygen is a greenhouse gas that would have continued to crank up the temperatures on these worlds, perhaps leaving an environment not too different from what we see on Venus. Now, moving outwards, it could be that by the time we get to planet E, so TRAPPIST-1 is the star, it's that A that we don't associate the letter A with. B is the closest in planet. C, D are the next ones out. E is that 4th planet from the sun. It's possible that E was just far enough out that it escaped that greenhouse gas fate. And as we continue to move out, F, G, and H may be, well, icier worlds, glaciated, or perhaps small Neptunes or Uranuses. To fully understand what's going on, we do need a telescope that we don't have today. We do need that terrestrial planet finder, that James Webb Space Telescope, that W first with a chronograph. So here is to hoping that these telescopes someday launch and bring us the science to help us understand just if this little M dwarf star does in fact potentially harbor life. Now, continuing on, I have a story from the outer solar system of, well, our solar system, the outer parts of our solar system. Researchers at the University of Zurich have used the NCCR Planet S simulation to try and understand how worlds like Uranus and Neptune can end up having moons. It had long been thought that these worlds weren't massive enough to form moons in a disk of gas and dust that formed around them during the early parts of our solar system, back when we referred to our solar system status as a solar nebula. During this early phase, a young star that was still pulling in gas and dust from the surrounding cloud and had massive jets of material flying off the poles. During this phase, that young sun would have had a disk of debris around it. And in some areas, you ended up with rocky worlds like Earth, Mars, all forming. And through massive collisions of objects like our proto-Earth and a Mars-sized world, things like our own moon got formed. Our moon didn't form next to the Earth. It formed through a collision with the Earth. Now, a collision with Uranus wouldn't have been able to form the 5 major moons that we've so far been able to detect around it. And Neptune doesn't seem to have a moon system. It just has Triton, which appears to be a captured Kuiper Belt object. Trying to understand how these two very similar worlds ended up with 2 very different systems of moons around them has been something that's been greatly perplexing. Now, using the NCCR Planet S simulation, scientists were able to calculate out that it's possible that in some situations you do end up with the system. So here we see that early gas and dust disk around an early sun rotating. If we take a cutout through the side of that gas and dust, it's possible that even low mass systems like Uranus and Neptune had eddies in this density distribution around them. And in those eddies, these moons could have formed. Now, this explains Uranus, but the question is, what exactly explains Neptune? Well, the answer could be that in the process of capturing Triton, in the process of capturing this Kuiper Belt object, the orbital interactions actually sent those, well, lighter weight moons on their way. Triton's a fairly massive object. It's not too different than Pluto in many different regards. And it's now thought through these theoretical models that Uranus could have formed its moons in situ, and Neptune may have once had moons, and those are now castaways that maybe someday we'll identify out in the outer parts of our solar system. Now, continuing to walk our way towards home, I'm going to make our way towards Mars. Our next story is of Mars moon Phobos. This little rock is only about 27 kilometers wide. And one of its most, well, dramatic features is a crater called the Sticky Crater that's 9 kilometers across. This particular crater has, oddly emanating away from it, a whole system of weird ridges and cracks. Trying to understand these grooves has been a problem in planetary science since they were first detected by the Mariner and Viking missions back in the 1970s. Now, it was easy to start out by hypothesizing maybe these grooves are related to this crater right here. My hand is on the crater. Maybe these grooves are related to that crater. But the issue becomes, how do you explain that some of these grooves overlap one another, and in fact, some of the grooves go through that crater itself? Well, in new research coming out of Brown University, Ken Ramsley and his team have done models of, well, what exactly would happen if boulders were sent flying from that crater during its formation. And in these complex models, they took into account, well, the specific gravity at different points on Phobos's surface, as well as the slope of the surface in different places. They had three specific things that they had to try and explain. They had to explain how do you get grooves that go across the crater itself? How do you get grooves that crisscross? And how do you explain a dead patch? And I need to cough. I'm sorry, I'm fighting a terrible head cold while trying to do this report. Okay, continuing on. So they had three things that they had to try and explain. The grooves crisscrossing. I'm still losing my voice. One moment. Okay, we're going to continue on despite the coughing so hard my eyes are watering. So they had to explain the grooves across the surface, the grooves interacting, and a section of the surface where there was a dead space on the surface. And the way they were able to explain this is the dead space, which is shown in the bottommost set of images. I can't figure out how to point. My hand's going off the green screen. The dead space was due to a low area that had a high lip around it. So it's thought that boulders that were running towards that low space hit the lip, took off, and flew a ways across the surface. Now, the craters, the grooves that went through Stickney crater, those were actually caused by boulders that came out the crater on one side and then went all the way around Phobos and entered the crater from the other side. Then, to explain the crisscrosses, it's very similar. In this case, you had craters that went all the way around the world from different angles, thus creating grooves that crisscrossed each other in different points in time. So this is a really cool piece of science, and I love that computers are finally powerful enough that we can do this research. Now, this starts to bring us to today's big story, which is the landing of InSight on Phobos. Now, to understand why we sent InSight to do this, we need to start out by understanding what the research goals are. And I'm going to drink some more of my tea. One moment. I'm going to get through this. There is a spacecraft landing today. This is exciting. The science will go on. Okay, so 3 to 5 billion years ago, Mars and Earth had very different gravities. They're very different sizes, but they both had strong magnetic fields. We see in Mars rocks fossilized magnetic fields that are baked into the solidified material. we see looking at Earth, we've got a magnetic field. It's still here. We look at the fossil record of Mars, or in this case, the geologic record of Mars, and what we see is there are formations that appear to be rivers, that appear to be ocean beaches that are all left. Thank you so much, Blue Cobalt, for the follow. We see in all these different things the signs that Mars, 3 to 5 billion years ago, had that warm, wet, planetary existence that Earth has today. And the question is, how did we go from two worlds that were similar to one that is full of life and one that, well, maybe full of death if it ever had life at all? Trying to understand this, we really need to, well, get to the core of things. And in this case, it means we have to get to the core of Mars. Now, we can't even get to the core of Earth literally, but we can get to it through secondary measurements. In this case, we measure the inside of our own planet using seismic waves. When there are massive explosions on Earth, when there is fracking, when there are naturally occurring earthquakes, when there are naturally occurring volcanoes, all of these different things that shake our planet send waves through our world. Two different kinds of waves get observed. There are the slow waves, which are called S waves, and these are waves that are actually sinusoidal in nature, and they can't pass through liquids. So they instead, well, will bend around and go through other parts of our planet. Then there's the primary waves, the P waves. These are more like acoustic compression waves that will shock through both solid rock and liquid inside our planet, going all the way through the core if you have a shock on one side of the world and a detector on the other. By mapping travel times of these two different kinds of waves to seismometers scattered all across our planet, we've been able to build up a very detailed picture of the internal composition of our planet. In fact, at various volcanoes, they're even able to put seismometers all over the volcanic system and map out the magma chambers within the volcanic system. Now, with Mars, we haven't had the ability to do this until now. In just about an hour and a half, we are going to have the InSight mission going in for a landing on Mars. NASA's going to begin their coverage in 30 minutes, and we are going to be co-streaming it here live, and I'm going to be staying here to answer all your questions. Now, InSight is going so that we can try and understand how these two worlds got separated by mapping out the inside of Mars, by deploying a seismograph that was built by a team in France. This particular seismograph is not the only tool they're taking. They also have various radio experiments that are going to allow them to precisely measure the wobble of Mars, and they also have a thermal instrument that they're going to deploy that is going to bury itself several meters below the Martian surface over the period of several weeks. And by making these measurements, we're finally going to be able to say, yes, it is warm beneath the surface, or no, actually, it's all quite cold. Now, the trick is it has to land. The mission has already made one orbital correction. After its many months flight to Mars, it was about 11 kilometers off course. They have made the needed corrections, and they are ready to see exactly where InSight is going to land within its 140 kilometer long landing ellipse. They are looking to land InSight in Eleusis, Planitia. This is an extraordinarily boring plane on Mars. As you can see in this image, there aren't really that many craters. There's a few fault lines passing through it, but in general, it's a nice, boring area. This is particularly necessary because they need to be able to just smack down that seismometer, bury in that thermometer, and they don't want to have to be dealing with the rubble piles we see in other areas on the red planet. Now, this particular spacecraft is too heavy to land as a beach ball, as Pathfinder, Opportunity, and Spirit all have done in the past. It, however, isn't going to need to do something quite as terrifying as what Mars Curiosity did with the Sky Crane. What this particular spacecraft is going to do is it's going to first aerobrake through Mars' very thin atmosphere, doing all it can to drop as much velocity as it can through the friction between that atmosphere and the spacecraft's heat shields. Once it's about 10 miles up, it's going to deploy a parachute. It's then going to drop to a few hundred feet, at which point it fires retro rockets and lands on those rockets, similar to how you may have seen a Falcon Stage 1 rocket land down at Cape Canaveral or on one of the barges. Now, this is nonetheless terrifying. I heard it described by one person that if that rocket turns off too early, it drops. If it cuts off too late, it falls over sideways. So that rocket has to end at just the right moment. And this is a high stakes mission. This is one that its previous launch was postponed by a number of years because it just wasn't quite ready to go. So after doing numerous tests, after making sure everything was just right, this is our final hurdle. We're going to land it now. We will know later this evening whether or not its solar panels deployed correctly. It's then going to take several weeks to deploy its thermal measuring instrument. And then all the new science begins to come in. This is a mission that I expect will be a major talking point at this year's Lunar and Planetary Sciences Conference in March, and I can't wait to see those science results. But first, we have to get through these next 3 stages. But before we do that, I'm going to take your questions for the next 20 minutes. So go ahead and at me in the chat, and I will do what I can to answer all that I can. As a reminder, this is the Daily Space. I am your host, Dr. Pamela Gay, and this show, like all the other shows here on this channel, is brought to you by the Planetary Science Institute, working in collaboration with Youngstown State University. We are supported through generous contributions from people like you. Every bit really matters, and from now through the end of the year, we have a major funding campaign going on. We unfortunately had been warned that our grant might be cut due to James Webb Space Telescope cost overruns and changes to policies at NASA. And rather than just having our budget cut, we had our budget zeroed. And we're trying to now raise funds so that we don't have to fire our entire staff for Christmas. So anything you can contribute would really help. There is information on all the ways you can help at the bottom of this screen. So check it out underneath this video. Okay, all that ugliness aside, I am now ready to answer your questions. So I'm going to scroll up through the chat and see what might have been asked earlier. I'm not seeing anything earlier. Okay. Thank you, DPI. That is fabulous. That is a fabulous sentiment, and I deeply, deeply appreciate it. And while I wait for those questions to get typed in, I'm going to say thanks to Blue Cobalt for the follow. Thanks Dat Dolphin for the donation. thank Saint Opus and H. Raven Rose for the follow. So Astro YYZ is asking, so TRAPPIST E is thought to be in the habitable zone. Yes. Hey, Rocket Sage. Yes, Astro Wise. TRAPPIST E is indeed in the habitable zone. It's not the only one in the habitable zone, but being in the habitable zone isn't enough for a world to be habitable. Venus and Mars are both technically in our solar system's habitable zone, and neither world supports life that we know of. And Venus, we don't know of life that it could support because it's like 900 degrees and rains sulfuric acid. In looking at the systems, looking at the planets in the TRAPPIST-1 system, worlds B, C, and D were all baked during the angry, hot, flare star period of the parent red dwarf star's youth. During those days, there would have been a great deal of ultraviolet radiation, there would have been flares, and there would have been added heat. And all of that combines to make the models show that these worlds most likely would have undergone some sort of a cataclysmic greenhouse event. Or worse than that, they would have just been completely baked dry. So those worlds probably not so habitable. The innermost one, in fact, so TRAPPIST-1b, is probably tidally locked and just one super hot world that is so hot that even sulfur clouds couldn't form in its atmosphere. So yeah, hot. It's bad. But E is far enough out that it may have escaped that fate. It may have been able to have that water vapor in its atmosphere not get ionized apart. It may have been able to have that water eventually rain out back onto the world, creating a new water planet not too different from our own Earth. And it's just kind of amazing that there may be Earth-like worlds out there, and it's just so frustrating that we can't yet observe them directly. So welcome everyone, and again, I am here to answer your questions. I am going to take a 5-minute break before the top of the hour, so I'll answer your questions for the next 10 minutes. Then I'm going to switch things over to the Mars Insight coverage of landing. As I said, I will be co-broadcasting everything that's going on, and I will be answering your questions and working to provide additional color commentary as we wait to find out, does the lander land? Yeah, it actually is indeed, Paranor, a break for more cold meds and to make more hot tea or something. DPI 209, those are all accurate words, but Hufflepuff implies vegetation. Not sure. So Miss Brick Kitten is asking, is the TRAPPIST planet in the habitable zone on an orbit to prevent it from becoming tidally locked, or do we not have enough information? So it all depends on initial conditions, on how smooth the world is, and it's not necessarily tidally locked that can be a problem. So to be tidally locked, it would probably need to be closer to the star. But let me back up for a moment and explain what tidally locked means. And I have a desk turtle to do the explaining for me. And I apparently have all sorts of turtles on my desk. So here is our turtle coaster that is our red dwarf star. I'm going to flip it over so it's not entirely turtles all the way down. Here is our turtle planet. Now, our turtle planet is not round. This means that when it tries to rotate, when it's oriented like this, it tries to get rotated over because gravity grabs extra hard on this asymmetry in its mass. So when it's rotating like this, on this part of its orbit, it gets extra torque. On this part of its orbit, it gets slowed. So all these forces add up to getting it to eventually settle in to always be staying pointed towards its planet. Now, for an example of tidally locked, you don't have to look very far. You just have to look up at the Earth's moon. It turns out that our moon's center of mass is not in the center of the moon. In fact, its center of mass is closer to the Earth than, well, to the other side of the moon. And this inhomogeneity, this unsmoothness in the density of material inside the moon means that when the moon tries to rotate, the Earth's gravity is constantly trying to pull it so that center of mass is closest to the Earth. And, well, early in the moon's life, it ended up getting locked towards the Earth. Thank you, Fenmil, so much for the bits. Thank you. You are awesome. Yeah. Tidally locked worlds need to be torqued. If you have a perfectly spherical world, it's not going to get tidally locked. If you have a world that is extra lumpy and bumpy, it's going to get locked down faster. Now, other things can slow down the orbit of a world. Venus has a really slow rotation. In fact, its day is longer than its year. It's kind of hard to explain this. There's lots of theories out there. Gravitational interactions with the Earth and other worlds are one thing that is used. Past collisions are another thing that is used. We don't entirely know how Venus got slowed down as much as it was. Similarly, Mercury isn't totally tidally locked and in fact has a weird resonance with Mercury. Mercury has a weird resonance with the sun. So lots of different things can happen in the rotation of a world. So it could be that some of those other worlds are in resonances not too different from what Venus and Mercury are in, even though they're not actually tidally locked. And with those kinds of really slow rotations, you end up with weird weather patterns. And weird weather patterns kind of make it harder to sustain life. So that's what I know. Do we have any other questions out there? As I said, I'm going to be taking questions for 5 more minutes. Then we're going to do a 5-minute break. I will keep the screen on and give you our standby imagery. And then we will be back for coverage of the landing. Thank you so much, Bad Panda Bear, for your resubscribe. Thank you for being here for 2 straight months. Can we light up the chat for both Fenmil and Bad Panda Bear? Thank you, everyone. Let's launch those rockets. Okay. Any more questions out there? Now, currently, Mars is roughly 6 light minutes away, which means we're not going to know exactly, did it make it? Until 6 minutes after it either has or has not made it. This is the kind of wait that really drives us crazy. We're going to be watching Mars in a variety of different ways, however. The spacecraft is going to be sending back radio pulses that should be detectable from here on the planet Earth, and we are going to have both Greenbank radio facility, Goldstone. Thank you, Michael. Thank you so much. Can we light up the chat for Michael? So we're going to be listening for InSight to send back its bleeps, both from Goldstone and from a Max Planck Institute in Germany. The Mars Reconnaissance Orbiter is going to be watching its landing to try and catch imagery, and Mars Odyssey, which launched all the way back in 2001, is going to be relaying satellite information. And we're also testing the ability of 2 CubeSats. Thank you, Elenice. Thank you so much. Can we light up, and AstroWise, can we keep lighting up the chat? And I'm going to scroll back to grab Steve's question. So we're going to be listening with all the things. So Steve is asking, even if you started with a spherical planet, wouldn't gravitational distortion be enough to eventually tidally lock given enough time? If it is a truly perfect sphere, there's nothing for gravity to grab onto. So you have to have some sort of an anomaly. Now, the truth is that geologically, you're not going to get a perfect sphere. So without having any naturally occurring perfect spheres in general, you always have the potential for tidally locked. But in theory, if you have a tidally locked world, if in theory you have a perfectly spherical world, it will not be tidally locked. So Aristotle's theoretical perfect sphere, never tidally locked. Had they done the complicated maths, Aristotle would have known the moon was not a perfect sphere because it is tidally locked. That was beyond the math of Aristotle. But it's just one of those cool things to think about. So Paranor is asking, could a black hole be considered a perfect sphere? Only if it's not rotating. So one of the really funky things about black holes is as they rotate, it distorts the space around them and flattens their I just lost the words, not their accretion disk, their event horizon. So this is how you can potentially get a naked singularity, is if it's rotating so fast that you end up with a very flat event horizon. So thank you, all of the people, for the bits. You guys are amazing. One more minute and then I'm going to go into a brief break. So Michael is asking, can planets get tidally locked in different resonances? So what I don't know is if that's still the same word. They can end up in different resonances, clearly, because Mercury is in a resonance. But what I don't know is if you refer to them as tidally locked into a resonance. So yes, worlds can get locked into a resonance. I don't know if nomenclature is friendly to the way you worded that. So yes, you can gravitationally lock a planet into a resonance. Yes, you can do it with different ratios. So we are going to go into a brief 5-minute hold, and I will be back at the top of the hour to bring you the pre-show coverage of NASA's landing of the InSight spacecraft, which is hopefully going to allow us to explore the innermost layers of Mars. Do not hold your breath until it lands. You will die. You can bite your nails though. So I will see you in just a few minutes. Go grab the snacks, grab the popcorn, grab the soda, and be ready to toast, probably with caffeine, to the landing of InSight. Thanks.